and as you said, we will go into the lower dimensions, to the nano scale, and we will have a look at the we'll have a look at some ferromagnetic multilayers and their property to host skyrmions and antiskyrmions. So first of all, this is a collaboration mainly between the University of Vienna and the University of Augsburg, and where I was supervised by my supervisors Claas Abert and Suess, and then from University of Augsburg, where the experiments have been performed, done by Heigl and Manfred Albrecht. So as outline, I will first give a short introduction to magnetic systems, to domain walls, and to these topologically protected spin textures. Then we will go to the actual research, which basically proves the coexistence of skyrmions and antiskyrmions in iron gadolinium multilayers. And we will see how we can nucleate these spin textures, and then also how we can extend the range of their coexistence. But since we are from so many different, let's say, fields of physics, I thought that I would just give one very short slide about how magnetic moments in a magnetic materials are basically are aligning, which in a ferromagnet would be that they will always try to be aligned in a parallel fashion. So here we can have, let's say, a magnetic, we have a magnetic system, let it be a thin film. And here the magnetic moments will always try to be aligned along the same direction, which is usually governed by the Heisenberg exchange. What happens sometimes is that, let's say, in some materials, if you don't have a magnetic field, then domains start to build. So we have smaller portions of this magnetic material, which within the small domains, they're all parallel, but of course they so we have multiple of these localized domains, and the transition between one domain to another does not occur as a sharp transition, but we have the so-called domain walls. And what's happening in this case is that, so let's blue mean that we have a magnetization pointing down, so let's say a -1 state, and red being a +1 state. Then a magnetic domain wall, basically, it's the transition from the down state to the up state. So, and this can either occur, like in this case, that we have this type of twist, or over a nail wall, which is again a magnetic domain wall. It's something very, very similar. Only the let's say the sense of twist, it's a bit different. So a nail wall is a direct 180 degree. So if we have a domain that it's not this large, but we have, let's say, we have here one domain which points down, and then here a second one which also points down, but we have a very, very thin domain in between. This domain, we usually call it just a stripe domain. So, and what happens is that we have a very thin region where the magnetization or where the magnetic moments are pointing up, and then over two domain walls, we reach again the negatively polarized state. And these three, let's say, type of transitions between the magnetization directions is going to be very important in understanding the topologically protected spin textures. And we will start again with the Bloch Skermion. So we have the Bloch wall, basically, that one could rotate 360. So if you take a line along this Skermion, then we would have two Bloch walls. And these spin textures are topologically protected because it's not, they're very, very, of course, if they would be absolutely topologically protected, we could not create them in the first place. But the idea is that from the point of magnetic, so let's say from this magnetic point of view, it's very hard to annihilate them. So we need very high energy barriers to overcome the so-called Bloch points, such that we can annihilate these spin textures, which are a local whirl of the magnetization. So we can have a Bloch Skermion, and we can also have a nail Skermion. Usually the Bloch Skermion, it's described as being dipolar stabilized, where Heigl skyrmion is mostly seen in systems with where the inversion symmetry is broken. So due to some antisymmetric exchange, for example, which we'll also discuss later, which is also called the Dzieloszynski-Mourier interaction. So then we can also have a bubble, a type 2 bubble. So usually skyrmions are then referred to as type 1 bubbles, but we can also have a type 2 bubble, which is just let's say here we have a small bump in the magnetization, we can say. So then the upper two, they have a vorticity of +1, and they also have, we can calculate the so-called topological charge, which gives us basically the two-dimensional windings. How many windings does this topology basically have? And in this case, we for the skyrmions, we obtain a topological charge of 1. But it also has a counterpart. In this counterpart, it's the antiskyrmion. And the antiskyrmion has not only Bloch walls or Heigl walls, it just has both of them. So what happens is that we don't have, as I said, so we have both of them. So we basically have both Bloch lines and Heigl lines, along which the magnetization transitions. And the vorticity and the topological charge of this spin texture would be -1. And now maybe the question is, okay, why are we interested in these spin objects at all? In 2013, Albert Fehr, Albert Fehr, who won the Nobel Prize for the discovery of GMR, has proposed the so-called racetrack. And the simple Skyrmion racetrack for memory application would be as following. We can have a very thin magnetic layer. Let it be a nanowire. So usual dimensions would be somehow 100 nanometers and only a few nanometers thin. And we can use the skyrmions to encode the information in terms of bits. So wherever we have a skyrmion, we would have bit 1. When we don't have a skyrmion, we would have bit 0. But the thing is, the information is then encoded in the distance between two skyrmions. So if here we would have a missing skyrmion, let's say we would have 1, 0, 0, 0, 1, the information would be given just by measuring the distance between these two bits, these two skyrmions, which might lead to some problems. So if you have a film with so let's say with defects or some small curvature or something like that, it might be that the velocity of the skyrmions, which are usually moved using some spin polarized currents, that the velocities won't be constant. And if the velocities are not constant, of course, the distance in between two skyrmions might change. So, okay, we can use some topologically protected spin textures to have the information because it might be harder to annihilate them and it would be safer to save the information. But to encode the information in the distance between this object, it's not reliable. And something that I discussed, so I briefly mentioned, it was that these Heigl skyrmions, which are mostly used, so they are stabilized by the Dzieloszynski-Mourier interaction. So it's an anti-symmetric exchange. And what happens is that, so you can have some heavy metal layer, so let's say some platinum, and then you can put on top some cobalt, and then at the interface between the ferromagnetic and the heavy metal layer, then this antisymmetric exchange interactions take place, and then the domains that are building, or let's say that the ferromagnet will favor a state in which it falls into domains, and these domains contain the Heigl walls, and one can stabilize skyrmions. But one can then also very easily create new skyrmions by some defects. So again, it's not maybe the best way to deal with it. In 2017, however, Montoya allies, they have shown that they can use iron gadolinium multilayers to achieve some sort of a new range of material parameters. So reduce the saturation magnetization, which gives you basically the strength of your ferromagnet, and the anisotropy constant. And then they achieved a new range where Skyrmions, but most importantly Bloch Skermions, were stable, and one had both clockwise and counterclockwise Skyrmions, and all solely dipolar stabilized. In the same year, Jagannath allies, they have experimentally demonstrated, or experimentally shown the existence of antiskyrmions, so the experimental proof that they exist in Heigl compounds with D2D symmetry, which is again a different type of DMI, let's say. So, and then together with the University of Augsburg, we said, okay, but it would be very cool if you would not have to rely on the distance between the skyrmions to write the information. It would be very, very nice to basically use both skyrmions and antiskyrmions and put them as 1 and -1 respectively to encode the information in ones and zeros. But then we tried something which was to take the system from Montoya. So we were again using iron gadolinium multilayers, which we know, okay, they can host skyrmions. And then for some part of the system, let's say, we introduced iridium layers. And this allowed us to further reduce the magnetization and the anisotropy in the system. And finally, we would obtain something like this. So we have here the, let's say, the reduction layers with iron, iridium, and gadolinium, and then in between just normal iron gadolinium, and then again the reduction layers. And with this technique, we were able to reach a new range of magnetic parameters, which we hope that will allow us to investigate further the dipolar stabilized spin textures. But the one thing that we had to also consider that iridium is also known to introduce some DMI, and so the Zhelezhinsky-Moria interaction, but also the interface DMI. And then the question would be, okay, but we want to have dipolar stabilized system, so we should treat this also carefully. This would be the experimental results. So we have here Lorentz transmission electron microscopy images, where we have a thin film, but let's say we have a thin membrane, and we apply an out of plane field, magnetic field, around 100 millitesla, and we are able to see counterclockwise Bloch Skermions, clockwise Bloch Skermions bubbles, but also type as a first order antiskyrmions, but also for the first time the second order antiskyrmions. So this would be the LTM contrast, and these are the simulated contrasts and directions. So now let's say that we know that in our system we can host all these spin textures. And the question that comes to mind, okay, but what mechanism stabilizes the spin textures? And this is where we made use of micromagnetic simulations, and where we basically came into the game. So I will also give a brief, let's say, summary of them, not summary, but a brief introduction to the micromagnetic theory, so we can understand better the simulations that we've performed. In reality, we have the small magnets, let's say. So we have the magnetic moments, which of course they are discrete. So we have a crystal lattice usually. We have a crystal lattice in magnets, and let's say that they have each have a magnetic moment. So it's a discrete space. In micromagnetic theory, we take this discrete space and then discretize it, use a continuous space. And so we transition from a discrete magnetic moment space, we transition to a continuous space. And here, the strength of the magnet is given by the saturation magnetization, whereas these white arrows, so the magnetic spins, they're all normalized, so they are unit magnetic vectors of length 1, and only their direction changes, of course, and the strength otherwise is just saturation magnetization everywhere. And in this case, we can also approximate all the other energy contributions, starting with the demagnetization energy, which is the dipole-dipole interaction between the, let's say, elementary magnets in this case. So if we have 4 magnetic moments, they would tend to join their magnetic fields and build closed loops. Then we have the exchange energy, which is nothing, it's just the Heisenberg exchange. So it favors a parallel alignment of the magnetic spins. Then we have the Zeeman energy. So we apply a external magnetic field, and in this case, the magnetic spin tries to be aligned with the magnetic field. Then we have the anisotropy, and in this case, so here we show the easy axis, so which means that the magnet will have a preferred direction in which would like to stay magnetized. So, and the uniaxial crystalline anisotropy that we have in our samples, it's a perpendicular magnetic anisotropy. So we have our thin film, so usually, let's say in the range of tens of micrometers. And the thickness, it's only 16 nanometers, but we have a perpendicular magnetic anisotropy, which means that it would, the ground state would be somewhere where the magnetization is in a polarized state pointing out of the plane. But we can also include the so-called asymmetric exchange interaction introduced in the form of the Jelasin-Skimoria interaction, and as we discussed, which rather favors a nail wall. Okay, and we can take these energies and then apply it in such a way, not apply it, but we can derive an effective field out of it. And this is the field that acts locally on the magnetization, on the unit magnetization vector. And we can use the Landau-Lifshitz-Gilbert equation to describe the temporal evolution of the magnetization of a unit magnetization vector, where we have two parts. So the first part would be the precessional movement, and the magnetization vector would then basically precess around the effective field. Then we have the dissipative part in terms of the Gilbert, the Gilbert damping, where the magnetization would actually like to, so if alpha is 1, then the magnetization just goes directly to the effective field. And in reality, we have the combination of the two, where through a dissipative precessional movement, the magnetization vectors will be aligned with the effective field, which again acts locally. So, and here, by material parameters such as saturation magnetization, exchange stiffness, or external field strength, anisotropy constant or DMI constant, we can include these energies in our micromagnetic codes. So, and first of all, we wanted to see, okay, we would like to investigate in which range the antiskyrmions or skyrmions are stable. And for that, we start with a small geometry of 300 by 300 nanometers. And we put in there a rough parameterization of an skyrmion or an antiskyrmion to analyze its stability, which means that we have the rough parameterization. Then for each set of parameters of applied external fields, saturation magnetization, anisotropy, and DMI constants, we relax the structure. So we numerically integrate the Landau-Lifshitz-Gilbert equation until no more temporal changes are visible. So, and then we can see if we have an antiskyrmion or a normal skyrmion when we calculate the topological number. So if you have -1, then we have an antiskyrmion, and if you have 1, then we would have a skyrmion. And if you have 0, this means that we have a polarized, so we have a ferromagnetic state. And this is what we did for a different range of material parameters. And what you can see here are phase diagrams where we varied saturation magnetization and uniaxial parameter, uniaxial constant parameter. And at 0 field, 10, 30, 50, 17, 90, and 110. And what happens here, you can see that there is a phase pocket where the antiskyrmions are stable. So we see this range where we have this blue color, so the topological charge is -1. And in this range, the antiskyrmions are stable when we start from an antiskyrmion as a rough parameterization. And with the increasing magnetic field, this phase pocket gets smaller and smaller until only a little bit of, let's say, stability region is visible. When we repeat the simulations with starting with a Skyrmions, then this blue region just transitions to red. So we have Skyrmion stable all over. Then we put all this information in one phase diagram, and we see the coexistent phase pocket of Skyrmions and antiskyrmions. So blue means that we have stable Skyrmions, and red would mean that we have stable antiskyrmions, and this region in between with the, let's say, pink or red lattice, we have the coexistence of these two. And the squares, the red squares, are experimental data where both antiskyrmions and skyrmions were stable. Here we didn't have any of them in experiments. And then again, blue and square in our experiments, we saw only skyrmions. And the triangles are the data, original data from the Montoya allies. So let's say that they went up to this part of the phase diagram. And by the additional insertion of iridium layers, we just went a little bit further to the left and down, and we were able to see antiskyrmions. Okay, now the reason of this of the dipolar of the relaxation mechanism, and we also then will write the DMI, which showed us that we have only a certain threshold where the antiskyrmions are stable, which means that if you have too much DMI in the system, then the antiskyrmions will not be stable, which again brings us to the following simulations where we have large scale micromagnetic. So this is a 5 by 5 micrometer film and about 60 nanometers thin. And we simulate a large film, so with these material parameters, with a little bit of DMI in the system, we see the stripe domains. We increase the magnetic field with respect to time, and then we are able to see, as well as in the experiments, we are able to see skyrmions, antiskyrmions, some stripes and bubbles. We increase the field, we get rid of the bubbles, we increase the field more, we only have skyrmions, and then we eliminate the DMI of the system, and we see the exact same behavior, which means that the Zhelezhinsky-Morier interactions are not necessary to stabilize the spin textures. Okay, so now if you have a look at how these spin textures are nucleating, let's have a look at the skyrmions first. We just have a stripe. So the stripe, we apply a magnetic field, it shrinks down, it gets smaller and smaller until it has to, let's say, separate from the other part of the stripe, and then we obtain a counterclockwise or a clockwise skyrmion. For an anti-skyrmion, however, we need a tripod. So we need three, let's say a stripe that joins three other stripes. Then we increase the magnetic field, we get rid of one of them, the second one, and the third one, and finally obtain an anti-skyrmion. Then we repeat the simulations with DMI, and we can see the same procedure. The only difference would be that we were able to see also skyrmion of second order.
Time is running out.
Yes, okay, I'm almost finished. So the last part that I want to show you was how to extend this coexistence, and this would be so if we have a thin film of 30 nanometers with very low saturation magnetization, then we are not able to see, so we can host skyrmions, but the stripe domains are too large, so our skyrmions would be too large. Then we can combine it with a larger film of let's say 400 kiloamps per meter, which individually they cannot host the desired scale, desired sizes of skyrmions. Then we put them on top of each other, and we create this 60 nanometer or 70 nanometers bilayer, which allows us to create again the magnetic stripes where the skyrmions and antiskyrmions can coexist in much better sizes. And we have published our results recently in Nature Communications, if you would like to have a look. So, and then to briefly summarize the results, so we have seen that in iron gadolinium multilayers, by the insertion of the iridium layers, we were able to achieve a new range of magnetic parameters where the skyrmions and antiskyrmions could coexist. In experiments, we have also proved the first demonstration of a second order antiskyrmion, and we have now also seen that, okay, it's all dipolar interactions. We don't really need DMI in the system, and we also provided a recipe on how to stabilize the systems, and one can also extend it by using nucleators and stabilizers as a technique, let's say. Thank you very much for your attention, and again, thank you also for the invitation.
We have time now, Professor Faber.
I would like to ask only concerning the name. Can Skermion and antiskyrmion annihilate in your case? I don't think so. Yeah?
This is a very good question. So, which I was actually asked also by Christoph a couple of weeks ago. So this is something that we should definitely look at. So I'm not very sure if they can annihilate each other, but since they have different topological charges, one would assume that because we have one and minus, also plus one and minus one could assume that they could indeed annihilate. So this is a possibility, but nobody's ever looked into it. So we'll have to see it.
May I ask you, with the Skermion, you cover S2, isn't it?
Again?
You cover
Yes.
S2, the sphere in 3 dimensions.
Oh, yeah.
Cover S2.
Yes.
And
Yes,
the
sir.
antiskyrmions, they have reversed covering. Is this like this?
Yes. I'm not sure if you can fit it directly into that. So because so I know only this magnetic part of the stories with S2 and stuff. I'm not very familiar, I have to admit.
Vectors, your magnetization vectors are unit vectors normally. You can see them as unit vectors covering
Yes.
an S2.
Yes. Okay. Now, yeah. I guess so. So
Antiskyrmions, I did not completely understand the structure of your antiskyrmions. So is this a reverse covering?
it's a bit different. So it's not only the reverse covering. Maybe it's just best seen here, because so this would be a Bloch Skermion. So we have this in the center. We have the core, and then it transitions slowly to the other state where it overgoes this clockwise
It's only half of
spin.
S2. It
So,
covers
but
half of S2.
yes, exactly. But the anti-skyrmion has them basically. You have to divide it in two, and then only then you could basically see this transition, which again could be divided into. So because we have not only one type of domain wall, but we have both of them simultaneously. It covers, I guess, two.
So it doesn't look exactly like the opposite quantum.
No. It's
Okay. Thanks.
thank you.
Can I have one question? Yeah, so in case of vortices in superconductor, if there is vortex and anti-vortex, the reaction to magnetic field is opposite, so reaction to electric field is in opposite. So do you have any physical factor in which your vortices your skyrmions can move? And do you observe opposite behavior of skyrmion and anti-skyrmion?
Yeah. So if we have, I guess I can explain best by. Also, if you have just let's say a regular nanowire where you have one skyrmion, then you can apply some spin polarized current. Then you would be able to keep the skyrmion on the track and then move it along the current. But with time, there is the so-called Skyrmion Hall effect, where it would start to drift to one direction. But anti-skyrmions, they won't move directly along the current, but rather 45 degrees. I guess it's between 30 and 45 degrees to the current flow. So they would start to move in different directions, as well as you said that in the case of the superconducting vortices. So they don't move in the absolutely anti-parallel directions, but just a bit different directions.
Mm-hmm. Okay, so my as you already expressed, my belief is that they can annihilate. The question is, what are the channels of energy release during annihilation? Are there phonons release or other channels of energy? But
it's a very interesting question that should I hope it's going to be answered soon. But it's very hard to simulate them in the first place together. So I don't know. I thought also after we talked at the conference, I thought about how to make them basically collide, but in terms of simulations, it's very difficult, and I guess in experiments even harder.
So please join the discussion table today. There's a round discussion table.
I'm afraid I cannot join because I did not calculate it's going to be on Friday, so I'm very sorry. But maybe another day I'll be glad.
Okay, you're welcome. Thank you.
Thank you very much.
Well, thank you very much.